LaTeX typeset would be the best. Um, I know that I only gave you guys a week to do it, plus there's the whole setting up the environment, all of that must have added some overhead. So at least for this one, I'm not expecting anything typeset or typed up, handwritten, or if you do it on an iPad or whatever, that's fine. Did you save your notebook? Uh, do you have it with you right now? I can look at it after class. If you're okay with that?
Can I ask a quick question on the homework?
Yeah.
I was just wondering on the question with this Sobel operator.
The written part?
Yeah, the written part.
Yeah.
When it says like no padding,
Yeah.
just put it like just where it fits on.
Right. You end up with a 2x2.
Okay, so you only keep those values that like fits on the center.
Right, yeah, because if you try to put the center of the filter at the top left corner, then like, yeah, you have an extra row and column outside. So that it's, because if I had asked you to pad it, then that will also be more calculations. So I figured just no padding. So yeah.
Thanks.
Sure. we're going to be picking up where we left off last class today. While we wait for people to trickle in, a couple of questions just to check in with you guys. As far as the code part for homework goes, does everyone have their environments set up? I know there were issues with Ubuntu. Is that still the case, or are we all good to go? If we do have issues, one of you can volunteer today, and I'll plug your computer in, or even if it's on Mac, and I can do it live after class, and you guys can follow along if you have problems. If not, then same deal as last time. You're free to leave when class ends. Homework. Okay. The other thing was Lockdown browser. Something I had mentioned during first week of class, and I also posted on Piazza, just a reminder to set it up in case you don't have it. Depending on how much material I'm able to cover today, my plan is to finish everything for panorama stitching up until Ransack, and then we'll have a quiz. That's if I'm able to get to the Ransack part by, say, 11:20. If it doesn't look like that, then we'll probably put it off. The third thing, regarding the project, so I had shared a link to a website that I like quite a lot. It's called Papers with Code. And the link that I had included on the post was to the computer vision section of that site. So the cool thing about it is that the way they've organized the website, if you haven't looked at it yet, actually, I'll pull it up. Mm, So this is the overall site. The link that I gave was for the state-of-the-art computer vision section. So the intent behind sharing this with you is so that you understand just the broad categorization of problems. Segmentation is separating background and foreground, or identifying outlines around objects, and there's various types of that depending on what setting it is. So tumor segmentation is more of biomedical image kind of problems. Just regular semantic is for scene images. Then depending on what method they're taking, it can be fully supervised or weakly or self-supervised, whatever. Similarly, representation learning is a broader problem that just has, I'd say it has to do with learning how to encode and decode a data set, basically. Classification, I think it's pretty self-explanatory. You have a bunch of images. You want to identify if they're animals or plants or cats or dogs or whatever. That's the simplest example for the problem. In addition to identifying what class, if you're also locating something within the image, then it's object detection and so on. So just giving this whole thing a bit of a skim will give you a sense of what is out there and what people are interested in. And if something jumps out at you, then you can look into it a bit more, and hopefully something clicks, feels like the kind of thing that you can build and probably add to. Yeah, so just to bootstrap the project idea process, I'd recommend taking a look at all the problems on here and reading up more about something that interests you. And with that, Let's dive in. Feature matching today. So last class, we talked about extracting features, which was identifying unique regions within images that we could use as reference points to then do something with it. In our case, we want to find how best to line them up such that the regions that are shared between the two images end up overlapping. So to do this, where we left off, we talked about patches of pixels and why those didn't do all that great when you rotated them because pixel values changed even though the actual feature is still the same. And we also need to have a way to remap our second image into the same plane as the first one. So rephrasing that a little bit, we have two images with overlap, and we have a way to identify unique patches, which is our Harris corner detector that we looked at last class and got all of these corners and putative candidate matches. The first problem, we still have a lot of unknowns because how do you decide which feature corresponds to which one in the second image? Visually, you could probably do it by hand, but I mean, that's not really useful to anyone. We want to do it in code. We also want to calculate the transform. And once we have the transform calculated, we need to be able to apply that to the second image. So the transforms that we've looked at so far, the final step that we had left off at was affine transforms, where we had coefficients for the x and y terms, but we weren't really doing anything with the w term apart from just sticking in an extra row at the end, which made the math a lot easier, allowed us to do translations, and even without that row, we were able to do other linear operations before that. The affine form lets us combine all of those. But for this particular case, if you want to put the two of them together, these are two different planes that are at an angle to each other. So none of the transforms that we learned so far would be applicable to changing the plane of the image. That's the first problem we're going to solve. And the way we do that is using what's called a projective transform. Structurally, it's not all that different from the affine. What's the change that we notice here? There's these two, all of these can now have values, right? Earlier, we had a 1 over here to keep that particular W term unchanged, and X and Y weren't contributing anything in the last row since the coefficients for X and Y were zeros. But now we're gonna add coefficients for that as well. Oh, this should be W over here. I'll fix that. Yeah, so once we add in coefficients that let us deal with the W aspect also, if you think back to what when we first introduced the additional row at the end and the W parameter, we said that that correlated to depth of the plane away from the camera. What happens if you change the depth of the plane as a gradient rather than a constant value? You have one side of the image going farther away from the camera and the other side at the same distance that it was. So you're shifting the plane, you're projecting it, which ends up looking something like that. So The matrix H, which has all the coefficients, is known as the homography matrix. And that is what we will need to estimate using our matching features so that we can then apply this transform to the image. Another little example of applying a perspective warp, which rotates it and also shifts the plane. Similar to, since this has more flexibility than affine transforms, the origin being preserved is not guaranteed, obviously, since it's more flexible than the affine, which also doesn't guarantee the origin being preserved. Lines still remain lines. Parallel lines don't necessarily remain parallel, because I think it's pretty intuitive when you look at this that the entire frame is getting deformed. So your lines are also going to have different angles between them. And if one half of the image is farther away, then stuff in that part of the frame is going to be smaller. So if you take ratios of scales of features from the part of the plane that is farther away and compare it with something that is close, your ratios are obviously going to be different. You can still chain these together so that they're closed under composition. One key thing to remember is that a homography matrix is defined only for a certain scale. So if you doubled every coefficient in the homography matrix, it is still going to be an equivalent transform. Applying it, so the transform P is effectively you're applying the homography matrix to pixel coordinates individually, same as we do for whatever transforms we've seen so far. When your target coordinates don't line up with the regular grid, one of the solutions that we saw before to deal with things like this was interpolation. Over here, it's a similar process where you add the contribution of the original pixel to each of the neighbors where the target pixel coordinates end up being. But that still doesn't guarantee that you'll have a complete image. This weighted contribution distribution is called splatting. And by doing this, we go back to our checklist and we now check off one item, which is the ability to project the second image to a target plane, but we still don't know how to identify matching feature pairs and what the actual transform should be. We know how to apply it now. Inverting the warp. So one way to do it is assuming you know what your second image plane should be, you can compare that with what the original one would be and estimate what the homography matrix of that is by just inverting this and solving for T inverse. If a pixel ends up in between two pixels, in this case, we would interpolate. I'll add that also. But this, while it is something mathematically, it makes sense that sure you can invert the transform, but problem is that we don't know what the right image should look like, right? We don't have both of those. We only have one plane which needs to be mapped to another one, and we don't know how to define either of the planes. So while we have the operation, there's still more to the story as far as getting the actual transform goes. So to do that, we need to match our features, and we also need a way to represent the features that are robust to transform, since we saw that patches had the problems that it did. Simplest way to go about matching two images, the basic principle is pretty similar to a lot of similarity approaches that we've taken. We have two patches, we can subtract them from each other. We don't care which of the two images is contributing how much, so we get rid of the sign by squaring it. And that gives us the L2 distance between the two patches, F1 and F2. In the case pictured over here, the two patches are pretty similar, even though they're not coming from the same region in the image. Whatever is within the window is pretty similar. So the L2 distance, when you're subtracting both of them from each other and squaring it, it's going to be similar enough that the final value will be pretty small, even though they're not from the same region. And that is a problem, because ideally, we want our features to come from the same region, because if they don't, then our transform is not going to make sense. So that's an edge case using the distance metric. In addition to that, we have another challenge, which is that we have a whole bunch of features in both of the images. So just brute forcing it, you would start off by calculating whatever distance metric. In this case, we're using L2, there's others. Comparing that for each and every combination of pairs, and that's computationally intensive, and we don't like that. A better way to do it, we still use L2, but instead of using the raw value, we look at ratios of distances. So F2 and F2 prime are two features in the second image, and F2 prime would have the second lowest L2 error. So by doing that, in the case where you have ambiguous matches, assuming that the other one is coming from the right place in the image, when we have ambiguous matches, the ratio would be high. So this solves a couple of problems for us. Our best score doesn't change, since we're still using the L2 under the hood to get our distances and rank our features. But since we're taking the ratios, when we sort them, the order that we get, it is sorted from best to worst. And when something is sorted, the good thing about it is that we can threshold our values and discard ones that aren't good enough. What this gives us is something like this. We have our reference image, we extract a bunch of features from it, and we're able to find correspondences. using the ratios, and these are thresholded to get rid of weaker correspondences. Sorry, there's some issue with my slides. Okay. So we saw we had 58 matches over here, which were after thresholding by the ratio score. With a slightly lower ratio, we end up with 51 matches, and we have an outlier here. So that doesn't really agree with what we're looking for. And this is a problem, but which is something that we'll solve using a different, more elegant approach. But first, we mentioned thresholding. So that's a value that we have to choose. Choosing values, sure, you could just pick a random number, use that, but that isn't informed, and we don't know how that's going to correlate with what type of matches we'll get. So we need a more informed way of picking a threshold. The way to do that is by comparing what's called the recall and specificity. And what this effectively tells you is the relationship between true positives, which is our real feature pair matches, versus our outliers at each threshold. So if you only do this for one threshold value, you get a sharp curve that has one point of inflection and a sharper angle. And the more thresholds that you sample, the more points you get, and it ends up being a smoother curve. So for an ideal approach, an ideal function that is able to find only true positives and no false positives, it would just go all the way up to 1. By finding the tangent of this curve, or where the slope is 45, that gives you a trade-off point, and you already know what threshold value resulted in this particular point, since it's using those values that we plot the curve. We can use that to pick our threshold that trades off high enough true positives with low enough false positives. So we're optimizing for both of those. By thresholding the match distances at different thresholds, we get sets of matches with different true false positive rates, and we generate the curve by computing rates at a set of threshold values through the full range of thresholds, which is why our curve is smooth. Area under the curve, the greater the better, which means you're capturing as many true positives as possible and minimizing false positives. That now gives us a bit more of a footing in terms of matching our two images and understanding how to reproject the second one, because we now have feature matches. But that still leaves the problem of representation. So we talked about pixel patches, rotating them changes the outcome. And ideally, we want something that is able to withstand changes or still give us the right feature despite transformation. So just to recap really quickly, some of the types of transforms that we know of are rotation and scale, which fall under the geometric transform umbrella. And there's photometric, which is things like intensity and color changes. So if we need a few terms to understand or talk about how features are robust to these transforms. So we introduce two new terms, which is invariance and equivariance. So the difference is not a lot. Invariance just means that regardless of what transform you apply to the image, your features are still going to be the same. Equivariance is slightly different in that if you have two transformed versions of the same image, the features will be detected in corresponding locations. So it has more to do with repeatability than the feature on its own not changing. And the line separating these two terms isn't very well defined. It depends on what source you're referring to. Some of the literature uses both terms interchangeably. Our Harris detector, let's think about what happens when we use corner detection. So if you have this particular object in an image and you run the detector on it, it is going to get corners in the first image. And assuming everything in the image is translated by the exact same uniform amount, all their features are also going to shift by the same transform. So corner locations are equivariant with respect to translation. And when we talk about rotation, while our positions are changing for corners, the eigenvalues for each of those corners, which is the direction of intensity change in the gradients, that still remains the same, since that's where our corners are. So corner locations are equivariant with respect to rotation. Intensity, however, if we change intensity, that is also going to change our gradients. Adding something directly to the values, since all of the values are changing uniformly, in that particular case, your gradients remain unchanged. So you have a dark region, you add 30 to it, you have a bright region, you also add 30 to it, but the relative difference between the two, or the rate at which it goes from dark to light, is still the same. But if you multiply it by a value and you have a pixel of, say, value 20, and you have another pixel of value 100, difference between them initially is 80. You double both, and your difference is now 160. So your gradient is steeper. So that is corner detection. Since it relies on gradients, it's only partially invariant to intensity change. If you have a gain to it, then it's no longer invariant. Yeah, so this is a plot of intensity values, and when you multiply it by a constant, then your threshold would also change. And so with the gradients, it gets steeper. For scaling, if we have a corner that fits within our window, but then we rescale the image so that this is what the image used to be, blown up, but our window size remains the same. So when we run our Sobel operators to check what the gradients are, you're only going to get an edge. So corner detector, Harris corner detector can only work at a certain scale the way we're doing it so far. To handle scale, we need to find the scale that gives the local maximum of f, which is our corner detection transform, the operator. And we need to be able to do this for both position and scale. So one approach from 1996 by Lindbergh was, so the problem that they're trying to solve is that we don't know what scale our feature is in. Corners can be at any scale of the image. So how do you deal with that? Instead of having a fixed window size that expects a certain scale, you just have a bunch of scales of corner detection operator windows and convolve it with the image. And that creates a scale space, which is the original image and other larger and smaller scales of the same image. And then we find our corners in that image scale space set of images, and then identify our Harris corner response for each pixel in each scale. There's a lot of computation since we have a lot of windows of different sizes. We should be able to do better than that. So any guesses on, it's a really simple change that we can do to the way we're handling this. We have an image with multiple sizes of windows. What can we change to this set of an input and operators? We're talking about different scales. There's something that we've covered in class before that we can apply here. I can give you a hint. It's got the word Gaussian in the name. There's a Gaussian, something that we built to deal with things of different scales. Yep, Gaussian pyramid is right. So instead of keeping our image at a fixed size and changing the size of the operator, we build a Gaussian pyramid and keep the size of the operator window the same, and look for corners at all scales in the pyramid. Another way to extract features is called the blob detector. At least that's how it's implemented in most libraries. But under the hood, it's a Laplacian of a Gaussian. So a Laplacian operator is a second order differential operator, which describes how quickly the gradient changes. This is defined for continuous space. So we use a discrete equivalent. There's two popular versions of this. One is called the 4-connected kernel. The other one is called the 8-connected kernel. And does anyone want to hazard a guess on why they're called that? You're on the right track. Just could you be louder? Uh, so if 4-connected and 8-connected, from the name, it should tell you something about how so kernels are applied to one pixel at a time, right? The center part would be on a pixel, and then you have 4 other pixels in its neighborhood that are influencing the output value of that pixel when you apply it. So it's connected to 4 other pixels. So it is de-emphasizing whatever is vertically and horizontally near it, and emphasizing the pixel that it's on. So there's 4 pixels connected, and here it's doing it for all the other 8 pixels in the region apart from the center one. Applying that over scale space gives us responses, which we can then use to get our blob features. We still haven't dealt with rotation. We talked about scale so far. So ways to deal with rotation. We know that our eigenvalues are still preserved even when we rotate a patch. So we find the dominant orientation, which is the principal axis of that patch. And we do that using the value of the larger of the 2 eigenvalues that we are able to extract. Another way to do it is we smooth the gradient and look at its orientation, and then whatever, so we know the center of the patch based on our corner response or whatever response function that we have. If it's blob features, those are represented as circular regions, so not applicable in that case. But when you have a square window, you can then use that applied to angle to rotate your window and define new coordinates for the region of interest. A more comprehensive approach that is a named algorithm, MOPS, multi-scale oriented patches descriptor. This is our first step towards an actual descriptor rather than using pixel patches. So using whatever response function that we choose, we find where candidate corners are, and after thresholding it, we take a 40 pixel window around the feature and downscale it to 1/5 of the original scale, and then sample that 8x8 window centered at the feature. A final step is to intensity normalize the window. We subtract the mean and divide by standard deviation within the window. And this incorporates rotation information across scales. Doing it for the entire image, we get a whole bunch of candidate samples. These are done at 5 scale levels. we still SIFT is the one that you'll probably see the most once you actually start applying things. It's been around for a while. It's really popular because it's fast and features are really robust compared to all the other kinds that we've seen so far. The reason it works so well has to do with the way those are extracted. We take, in this case, we're talking about a 16 by 16 window, and we divide it into a 4 by 4 grid of cells. And for each cell, we have a gradient corresponding to it, and those get combined into a descriptor that aggregates the contributions of each individual cell's gradient values into one vector representation. So there's 8 descriptors for orientation because we have our x, y, z coordinates. And then there's 16 cells that we were starting from, which we're aggregating into this 4 by 4. So that gives us a 128 dimensional descriptor. It's 128 elements in a vector, and the position corresponds to contribution of a certain direction per cell. So that representation doesn't change no matter what you do to the image, whether you rotate it, translate it, scale it, whether illumination changes, it condenses all gradient information into descriptors. And that is what we need. An example of how well something like this performs. This is the same place, day and night. Here we have occlusion because we have people in the front of the image. Here the view of the scene is unobstructed. Illumination is also different. There's a really bright patch over here. Here the lighting is more uniform, even though intensity value overall is, the image is darker, but it's still able to extract features in there that correspond pretty well. Back to our checklist. We now have the ability to warp. We also have the ability to estimate what the transform should be. We have a way to match corners, and we have better feature extraction. So if we put all of this together, we can use SIFT to extract features, which gives us key points and their corresponding vector descriptors. We can find which one of those are matches with each other by calculating the L2 distance between the descriptors. We can then filter by using a threshold score that we determine using the ROC curve. We can estimate what the transform matrix to apply projective transform should be using pairs of matched key points. And we can finally warp our image by applying whatever we get out of here to the second image so that it is remapped to the same plane as the first image. There's a problem here though. So estimating the homography matrix, although we're able to do it, the way we're doing it right now still involves iterating over all pairs of candidate matches and looking at their distance scores to decide if they're good matches or not. And we also have the problem of outliers that we still haven't dealt with. So effectively what we're doing is this, where these could be, you can think of this as distances between pairs, and we want to find a relationship that effectively minimizes distance between feature pairs for as many pairs as possible. The way we're doing it right now, it's not guaranteed to give you the best line, since it takes into consideration the overall distribution of feature pairs that we have and distances. And we want something that can also factor in there being outliers. So one way we can do that is, given a hypothetical line, we pick feature pairs and plot lines between them and count how many other features are within a certain distance of the line. So we draw little perpendicular lines connecting our hypothetical line to whatever features are nearby. And if they're within a certain distance threshold to our candidate line, we say that those are inliers and the others are outliers. So we calculate this for a bunch of lines and count the number of inliers that we get, and we pick the best one. So there's a couple of things that we don't know about this. One of them is how many rounds of trying out lines do we do? And how do we represent this whole sequence of operations mathematically? How do we find the best one once we have our candidate lines and their number of inliers? The algorithm that we'll be using to do this more formally is called RANSAC, which is Random Sample Consensus. So we randomly pick feature pairs and count how many inliers we get along the line joining them. We check if it's above a threshold or not. If it's above a threshold, then it's one of our good lines. And we keep doing this for n rounds, where n has to be greater than or equal to this relation, which is defined using the probability of getting a match. E is the proportion of outliers, and S is the sample size. So total, however many features you have, is your S. E is what proportion of that is acceptable as outliers, which there's still a bit of trial and error, but this narrows it down a little bit. And when you have the right number of rounds, we're able to find a good set of candidate lines. RANSAC will not work if you have more than 50% outliers, because then if your outliers are the majority there, you can't really call them outliers. And this formulation breaks down for that. With all the inliers that we have, the assumption is that whatever transform all of those inlier heavy lines represent will be similar enough that we can average the translation vector over all inliers. And that gives us our final best transform. Pros and cons of using RANSAC. Pros are that it's a simple process, it's iterative, simple to conceptualize also. You can apply it to pretty much anything that requires picking a best function from a set of candidate functions. And computational cost is acceptable. The downside is that we need to decide how many number of rounds based on what an acceptable number of outliers is. And based on that relationship, the number of rounds required might be too high if your sample space is large. And if you have inliers that are, if you have fewer inliers than outliers, then it breaks down. And ultimately, this is a brute force approach since we're iterating over feature pairs and picking ones at random. It is also an example of a voting-based fitting scheme, which is where the consensus in the name comes from. Putting all of this together, we now have a panorama stitching pipeline, so we can detect features using Harris, SIFT, Blob, whatever. There's a whole bunch of others. There's HOG, which is histogram of gradients. There's ORB, which is used a lot in Visual SLAM. We are also able to match features using the ratio of distance ranking. We can threshold their targets. We're able to compute homography using RANSAC and then apply the transform, which gives us our stitched panorama image. Okay, so we can start at 11:30. We're going to do a quiz today. I know the panorama stitching pipeline is a lot. There's a lot of steps, but this will be the next homework, and I'll structure it similar to the way I did for homework 1 with a skeleton and write-up and everything. So hopefully once you actually implement the whole thing, that will cement all of these individual pieces. It's a lot easier to keep track of what's going on when you do it. I hope everyone has Lockdown Browser. There was one student who isn't enrolled for the class yet. She is not here. Okay, so that takes care of that particular problem. If you go on UB Learns, assessments should be in quizzes. This should show up. Can someone confirm that you're able to see the quiz on UB Learns? Oh, okay. Okay, so what I want you all to do is just start it, see if it opens up your Lockdown browser. And it should ask you for a password to start the quiz. there's nothing in the quiz that's from last class. It's only everything up until last week. And there's, I think, 22 questions and you get 20 minutes. They're fairly easy, so just um, keep in mind how many questions per minute, a little over one. Are we all at the password stage? No issues with lockdown browsers, everyone in? Anyone with issues, show of hands? Yeah, what's going on? Yeah, I'm coming. Yeah.
The lockdown browsers.
It's in quizzes. Yeah. Could you open that up? I just want to see what it looks like for you guys. Yeah. Yeah. Was loaded. Okay. Password. Who else had issues? Yeah. Oh. Yeah, we still have a couple of minutes. I'll check back in with you. Just loaded. You raised your hand? What's going on?
Once the lockdown browser is happens when the starts in the background.
I think, can I try something? What's the shortcut to?
That's why that is close this time,
Mhm.
but it's working fine.
But this is not lockdown, right?
No, this is not lockdown. This is the Chrome. When I start the test.
Uh, oh, could you close it out once more? Lockdown. And
This?
yeah. And could you like get out of full screen? Can you try quitting Chrome?
Yeah,
Can I try? Oh, do you not have your?
no, it's quit.
Uh, how do you?
Open Chrome.
Yeah. Oh, it's still. Okay. If that one other person Is it working for you? What's going on? Oh, well, in that case, I guess I'll disable it for this one quiz. Uh, yeah, issues with lockdown? I'm gonna disable lockdown for this one. Oh, uh, yeah, maybe try refreshing and quit out of lockdown. Um, go back to the quizzes tab, just open it up normally, and yeah, do the quiz. I believe it should still ask you for a password, so does everyone have the quiz open now? Not in lockdown, just regular browser? Okay. Password for the quiz. You must start. You've got 20 minutes from the time you start. Oh, you're still. Got it? Okay. I am fine. Is that working for you?
message from Piazza. I don't know, is it from you or is another TA is saying some of the code is like not right and with another sequence of code to replace it. I don't know, it's just for me or it's just for everyone. It's like the last
I
one
didn't.
is showing.
Can you show me? Oh, to replace that one line in the code?
Yeah.
Yeah, that is for everyone.
Oh, okay.
It-
Yeah, I
it-
just want to make sure that this is on the email, just saying you, the message is sending only to me.
Oh, yeah.
Okay, yeah.
You're fine. Okay.
For the afternoon and when we rotate and lunch, I'm getting some grid lines. I think is that fine or is it supposed to fill in that? That's one big question.
Grid lines as well.
Not sure, I'm getting some lines in the image after rotation.
You committed it, right?
I have my separate branch. Yes, sure. Okay. I'm in the dev branch. The branch. The project is.
I'll only be looking at the main branch at the end.
Okay.
Mm. Yeah, that's fine.
That's fine.
Yeah.
It makes creative, so I use my personal name and it's fine.
Oh, what's your name?
Maybe
Yeah, I saw
waits toward the.
there is 2 GitHub accounts.
Oh, this is the like I use.
Yeah, I linked it to your UBID yesterday.
And I have one more doubt. Is it fine like this one? Because this is not what you gave in the React site, something different.
Yeah, that's fine.
This one, right?
Yeah.
And you didn't give me any example for the shared. You just gave the example for the first 8, I think.
Oh, okay.
Can you just give this over or is it fine?
Yeah, I mean that looks like what is in the slides, right? I'll add output for that.
That's
So basically, while giving the quiz, can we access the notes which are written on the iPad?
Uh,
I did not access it today.
I mean, from the
So generally
the,
take
the
notes.
kind of questions that those were, I think you can infer what the answer should be from what's in the question usually. So closed book is how I had intended it.
So we can check.
No.
project purpose. Can we also use like CDP or any other?
Yeah, whatever. That's
So currently, it may be a papers with code.
Papers with Code was just for someone who has no exposure.
Yeah, sure.
So if
I
you're
have
familiar
plenty
with
of this.
CVP at
I
all,
can just take the data segmentation and apply this.
what year is this paper from?
This is from 21.
Okay.
Should be okay.
Yeah.
So I
Fine.
haven't taken medical data or anything. Try to do image segmentation. Will that be okay? Like maybe a concern.
Mm,
Like you have blue money as data and all this. But if I apply this network on top of it,
See if you're using something like an MRI instead of what is this originally designed for?
this is
What
like
kind of data?
instant segmentation, actually, like basic semantic segmentation. This is for
Okay, so just
IDD.
flat 2D RGB images, right?
This is for actually the driving data set.
Okay.
So
Yeah, so
units are pretty common. So
if you switch from that to something like MRI data, MRI usually has 4 channels, so then that's a challenge that you'll have to address. So just something that makes your implementation a
different.
bit more than, I just swapped out pixel values in 2D images, right? Because if you're going from the cars, whatever the driving data set, flat 2D RGB images, if you're going from that to say X-rays, which is just again 2D grayscale images, then the problem isn't really changing that much fundamentally, even though it's a different data set.
Okay.
If you can think of something that adds a bit more to it, or let's say you go with X-ray, which is still 2D flat, you end up using a different loss function because you find that whatever it was using by default doesn't generalize well enough when you're using X-ray images or MRIs, because there's not a lot of intra-class variation, but interclass variation, but within a class, there's a lot of variation. So in that case, you would have to think of like fine-grained classification style approaches for your feature extraction. I don't know, just giving you examples of. Ideally, you should. There should be something that is specific to your problem also, in addition to just picking up an existing solution and applying it.
But image segmentation is a topic which we can take, right?
Yeah, sure.
And I also saw the post which you have like posted on LinkedIn related to some internship for a research one. So I did send a resume to it. I just
See, the thing is,
is it closed or not? Is what I want.
it's closed, and the kind of master's student that we're looking for is someone who will be able to like implement a paper directly without any supervision, because the objective is to take some of the weight off of me, since that it would have been something that I would have worked on normally, the project that we are hiring a master's student for.
I
But
mostly work on CV, but not on this area, mostly in the detection.
and there's also a hardware aspect to it. So like doing IoT type of. Currently, I do well, breast tumor detection is what I'm working on, and there's 2 projects related to that. But this is for a different thing. We're trying to do wireless 3D breast ultrasound, and it has a motion and inertial measurement unit, an IMU on top of the probe, and there's an optical tracker that we're using, and we're trying to estimate how to transform consecutive frames without information from the IMU or the optical tracker, using just optical flow between frames.
Like
And
Kalman filters, something like that we use for the
no, 1 second. Do you have a question? Yeah. Okay.
It's in assignment we have like for flipping 2 row-wise operation.
Mhm.
Was for column like last so maybe pixel-wise.
I mentioned that.
So
I don't remember. Yeah, pixel wise is fine. What is this for? This is the code part.
output is same because basically mentioned 2 row-wise.
Oh, I don't remember putting that. Yeah, pixel wise is fine. As long as your image rotates and you're doing it using an operator rather than a built-in function, I don't care. Yeah.
Coming to shearing part, shearing is it when I do shearing, it is like shearing from point at 0.0, top left is staying intact, shearing happening like shifting it. So is that correct, or does the bottom should remain intact and shearing should happen at the top? How we should, because in the slides
Ideally, it should be at the top. There's like you could chain operations to do that, probably.
because there is no sample
Like if you,
on
yeah, I missed that. So if you, wait, hang on, what was it, sharing sample? So one way to do that, I mean, I'd still have to test it, but if you flip X, Y both, shear, and then flip back, I think that would be the right output. I'm not sure. I'll add a sample regardless. Questions?
That project you have said, right, to make something like what kind of expectations are you with the project?
As long as you're not picking up a repo and running it verbatim on a different data set, like that, there should be, I mean, yes, one of the key reasons you would want to use a deep learning based approach is that it is generalizable to other problems, but in the interest of you know, making improvements that are domain specific. So if you choose a different data set, then there should be some knowledge that you can inject into the process, right? Just by virtue of knowing what problem you're solving. So yeah, just some change to the entire pipeline. It can be at any step, as long as you have an explanation to go along with it. Why you chose to make that change and why you think that change helps. That will be good enough.
So when can we put the proposal or something?
I'm going to write up the document asking for the proposal on Saturday and put it up on UB Learns then. So you'll get a week.
So it would proposal.
Yeah. So fall last year there were, I think, 2 checkpoints, 3 checkpoints. I'm not sure. So I'll have to plan that a little bit. Since it's 12 instead of 16 weeks, and I also have to think about how to interleave that with quizzes and homeworks and all of that. So it takes me the entire weekend to prepare for Tuesdays. So I'll have something out on Saturday. Yeah. What did you think of the quiz? Was it, like, in terms of difficulty, reasonable, easy, tough? Okay. Is there anything you would want me to do different?
One thing that after the quiz, you have
Yeah. That I think you should have. Like, did it show you the score when you were done? I think it did, right?
what the answer.
Yeah, I'll do that. No, what I was trying to ask was more about just in general course material. I know there's a lot of material and it's packed tightly. Is there, because my goal is to try to cover as many of the, like, important classical topics as I can. I the amount of time that I could spend on each topic, I mean, the stuff that I did till now, I could spend the entire semester on that also, but then you'll end up missing out on a bunch of topics. So the trade-off is something that I have to decide, which is what I'm trying to ask.
Can focus more on deep learning rather than this. I mean, right now it's but later in after the medicine and all.
Okay, yeah, that's sort of why I'm trying to.
Yeah, this is classic image processing.
My plan is, I think next week should be deep learning class. I don't remember yet. But I'm trying to stick to this as much as I can. Oh, image alignment. Yeah, week 5, pre-planning. And then after that, all of this is going to be in that context. A lot of it, at least. I might swap these topics. I'll think about it a little bit. Oh, I already deviated from my initial plan. Tracking. Okay. Yeah.
Yeah, that's
What-
basically,
what
I
was
just wanted to
that?
ask.
Oh, yeah.
Currently pursuing PhD under someone, right?
Yeah, I have 2 advisors. This is what we're trying to implement. It estimates. I think someone was waiting. Is there someone came in, right? Um, yeah, so we have these. We want to get this, and this is required in all of the scans that we've been doing so far, that we are using for our research up until this point, is acquired using an ultrasound probe that's fixed to an arm that is mounted on a motor, and it moves at a constant rate. So you know how much distance is covered, and reconstructing it into a 3D volume is trivial since you already know where each frame is coming from. We
want to recreate
now
that
want to switch to a wireless probe and let people do the scans themselves and get. So in that case, you don't know where the probe is, right, every time. And there's 4 things that talk to each other. There's the probe that sends frames to a tablet. There's the IMU, which sends position coordinates to something, a computer, can be a Raspberry Pi. And then there's also an optical tracker, which is connected to a third computer. That has, I think there should be a picture here, maybe. That also gives coordinates in 3D space, but the reason we're using that is because it's more accurate than using an IMU. An IMU is good for orientation, but not for if you want to get just linear position. You have to derive that from acceleration, right? Since acceleration is what an IMU gives, and that's not accurate. So this model, while we're training it, we also supply IMU coordinates and optical tracker coordinates and use that as the target translation along XYZ and roll pitch yaw. And the model learns to predict that from optical flow between pairs of images. And then ultimately we get rid of it and use just the model to predict these values instead of IMU or optical tracker. So this is something that a company already made. They're called Pure Imaging. Might be here. Okay, I don't know where the image is, but basically that company, they're using this already. So we want to do the same thing and improve it.
I actually wanted to know just that, basically. Yeah. Okay. Cool.
Yeah, since it's also a very like short time frame for the project. We have to, we're aiming to finish it by August.
Oh, for summer.
Yeah.
It will be a time crunch. But
Time crunch, and I won't be able to oversee anything at all, except for just walking someone through how everything talks to each other and what data we want, what outputs we want. That's about it. Yeah. Welcome. What's your name?
Athero.